Hello guys, and welcome to this new session. Today I'm going to solve a complete example on traverse adjustment from A to Z with all the details. So let's start. In a previous video I explained the main purpose of traverse and the data required, like the whole circle bearing of the first side and the coordinates of one of the stations, and also I explained that you need to measure the internal angles, these angles of your traverse, and the distances between each two stations, like this distance, this one, and this one, using total station. After that, I provided some information about the main stages for solving a traverse, and today I'm going to go in details through the solution. I mentioned that you need first to calculate the angular error and distribute this error, and after that you need to calculate the whole circle bearings, and I mentioned that the whole circle bearing is just an angle from north to the measured side. For example, if you are working on side AB, let's take this traverse as an example, ABCD. So the whole circle bearing for side AB, this one, it would be an angle from north clockwise towards AB. That's it. Very easy, very simple. So this is the whole circle bearing of AB. Okay, you will learn how to calculate now the whole circle bearings throughout this session. Let's take another example, the whole circle bearing of CB here. This is north, guys. Here we have, this is the north, and here this is north. I will apply the definition of whole circle bearing, which is an angle from north clockwise to the line that I'm working on. In this case I'm working on line CB, so this would be the whole circle bearing of CB, and so on. So this is the principle of whole circle bearing. For more details, I will strongly advise that you watch this video, the previous video, which is called Traverse Adjustment Part 1, Purpose and Observations Needed. This will provide you with a good background about the traverse, the aim of it, and what are the observations that you have to do, and what is the whole circle bearing. You will have a good understanding about all of these new terms. Also, I explained in the previous video that we are going to check the latitudes and departures, and these are related to the distances that we measured using total station. For station A and station D, let's say here, very simple how to calculate the coordinates. The aim of traverse was, guys, to calculate the coordinates of these stations, easting and northing of D, easting and northing of C, easting and northing of B, etc. And we will start from known coordinates. For example, if you know easting of A and northing of A, how to calculate the rest coordinates for B, C, and D. Just a quick idea now. What we are going to do today is very simple, guys. We are going to start from station A. Now you know station A, you know its easting and northing. To calculate the easting and northing for D, for example, this is easting for D here. Okay, so I will write down here, this is easting of D, and this is northing of D. And from the previous video, you know that we will call this distance along the easting axis. This is the easting axis. We will call this distance, guys, departure, from previous video. And you know also that we will call this distance along the northing axis latitude. So this is departure between A and D, and this is the latitude between A and D in this case. So our aim is to calculate easting of D and northing of D. So very simply, because we started from a point with known easting and northing, so you know easting of A here, you would be given this number. So easting of D in this case would be very simple. Easting of D would be easting of A, which is known, plus the departure between A and D. So this is a distance between A and D. So today you will learn how to calculate this departure so that you can get easting of D. So easting of D, for example, would be easting of A, which is known, plus the departure between A and D. And northing of D, very similar, would be northing of A, which is known, plus the latitude value between A and D. So this is a summary on how we are going to calculate the final easting and northing for these stations. And as I mentioned before, guys, before we measure these angles using total station and we measure these distances, so we are going to calculate the angular error for the angles and then distribute this error, and then we are going to calculate the linear error for the distances and then to distribute this error, and then we are going to calculate the final coordinates easting and northing for each one of these stations. Okay, so let's go now to our example. This is our example today, guys. We have 4 stations, A, B, C, D. We've been given the whole circle bearing of line AB. So this is the whole circle bearing of line AB. This is given to us to be 100 degrees, 11 minutes and 22 seconds. And also we've been given the coordinates of station A. Always you need to start from a station with known coordinates. In this case, coordinates of A, 900 meters for easting and 800 meters for northing. So these are known coordinates. Based on them we are going to calculate the unknown coordinates easting and northing of B, C and D, and this is the aim of the whole thing, of the whole traverse, calculating easting and northing of these 3 stations in this case. Keep in your mind that in this case we are working on 4-sided traverse, but traverse can have any number of sides. In fact, it can be 10, even 12, 15, 19, etc. So it depends on the size of your project, and the same principle you can apply on any number of sides or stations, but today we are going to work on 4-sided traverse. And then using total station we have done some measurements. We measured these 4 angles. As you can see here, this is angle A, this is angle B, this is angle C and D, and we've done these using total station, and I explained this in a separate video, how to measure horizontal angles and distances using total station. And these are the distances between A and B. This distance here, this is the length of AB, this is given here. Here we have BC, the length of BC, this line, the length of CD, this line, and finally the length of line DA, this line. So now using total station we've done some very important observations. These are 4 angles and 4 distances. Okay, and again you can find the details on how to do these observations using total station in a separate video called Measuring Horizontal Angles and Distances. So to solve the traverse, guys, we are going to arrange very nice table like this. So here first we would like to here write the station name A, B, C, D, and the side of the traverse, side AB, side BC, CD, DA. In this section we are going to transfer the numbers, the measured values of the length of each one, length of AB, BC, CD, DA, and then we are going to write here observed internal angles in degree, minute, second format. For example, if it's 68 degrees, I will write it like this: 68 degrees, 12 minutes and 26 seconds for station A. This is the internal angle at station A, and so on. So degree minute second format. And here in this section, guys, we are going to calculate the angular correction. So we are going to calculate the angular error and then here the angular correction values. Just trying now to let you understand this table, how it works in this table. So we have observed here some angles. We are going to calculate the angular corrections here and then to calculate the corrected values, corrected angles here. Once you have done that, you are going to go to the second stage, which is calculating the whole circle bearing for each side of these traverse sides. So we've been given the whole circle bearing of AB. In this case it was 100 degrees, 11 minutes 22 seconds. Just transfer this number here and then you will learn how to calculate the rest of the whole circle bearings. Once you've done them, you are going to work on the departures and latitudes in this section here. You are going to calculate the departures and latitudes values here, and then the correction for the departure and latitude, and then the corrected values, and finally you are going to calculate the final coordinates easting and northing of each station B, C, D, because we've been given the coordinates of station A to be in this case 900 and 800 meters. So here the corrected angles, and here the whole circle bearings, and here the corrected distances in terms of departures and latitudes, and then the final coordinates easting and northing. This is a summary of the whole thing, so let's get into it. Okay, so this is the traverse table. First I transferred the measured values given to us and the whole circle bearing for side AB, and also the coordinates of station A. These are all given numbers from here, guys. Okay, just I'm trying to transfer all of these numbers given to us to the table first. So the observed angles from here and the distances from here, the whole circle bearing of line AB is given to us here, and the coordinates of station A are given here. Just transfer all of these values to the table. Okay, as you can see here. Now we have our table ready to start the calculations. So in this line, guys, of the table, this one, I will calculate the summation of some numbers that I will need them, and here I will do some checks in this line. So let's start first with this relation. The summation of the internal angles should be, in theory, 2n minus 4 times 90. n is the number of the angles. Here in this case we have 4 angles A, B, C and D. So 2n, n would be 4 because we have 4 angles, minus 4 times 90 degrees. In this case it would be 360 degrees. So in theory the summation of these 4 angles, as you know, should be 360. This is easy. However, if you are working on a 5-sided traverse, n would be 5. If you work on 6 sides of the traverse, it would be 6, and so on. But in this case we are working on a 4-sided traverse, so now we are going to find the actual summation of our observed angles. The angles that we measured using total station, we are going to find the summation of all of them. And also I will need the summation of the distances, summation of these 4 numbers, the distance between A and B, B, C, C, D, DA, which is the perimeter of the shape that we are working on. So the summation of all of these 4 distances, which is the perimeter of this traverse, and we will need this number later on. So let me start here calculating the summation of 4 distances and 4 angles, and I will write down the answer here. Let me do the calculations now. So the first angle, 68 degrees, 12 minutes 26 seconds, plus 94 degrees, 42 minutes 8 seconds, plus 102 degrees, 58 and 47, and finally 94 degrees, 6 minutes 27 seconds. So the summation of all of these angles would be, in this case, 359 degrees, 59 minutes and 48 seconds. And the summation of all of the distances is here, 374.509 meters. Okay, so these are in meters because they are distances, and here we have degree, minute, second. Just a quick note here, if you don't know how to deal with the degree, minute, second format on your calculator, I would strongly advise that you watch a separate video called Measuring Horizontal Angles. I explained how to deal with this kind of units using your calculator. Now we are going to calculate the angular error, which is the summation of the observed angles. This number, guys, here, this is the summation of the observed angles, 359 degrees, 59 minutes and 48 seconds minus 360 degrees, 360 from here. This is the theoretical summation. In theory it should be 360. Okay, but when we have done the measurements, we've done some error, which is in this case the difference between these two numbers. So 359 degrees, 59 minutes, 48 seconds minus 360 degrees, and the answer in this case would be minus 0 degrees, 0 minutes and 12 seconds. So this is the error that I made when I measured these four angles using total station, which is 12 seconds in this case. So now we need to distribute this error value. Okay, guys, so always use the opposite sign to do the corrections. When we measured four angles, we've done an error of minus 12 seconds, as you can see here. This is the error, so the correction would be plus 12 seconds. We are going to add 12 seconds to correct this error. And because we measured four angles, we are going to distribute this number by 4. So 12 divided by 4 to get the correction value for each angle. So we have four angles. In this case, 12 divided by 4, it would be plus 3 seconds for each angle. So here the sign would be plus. So because the error was negative, the correction would be positive, and the value of the correction for each angle should be 3 seconds in this case. 0 degree, 0 minute, 3 second. So this is the angular correction for each angle. As you can see, it's very simple and easy. So the error that you made, in this case 12, divided by the number of the angles, and then you will get the correction value for each angle. Don't forget, you made a negative error, so because of that your correction should be positive, the opposite sign. So once you've done the correction calculation, now it's very easy to calculate the corrected angles, corrected value for each angle. For example, the first angle is 68 degrees, 12 minutes and 26 seconds. I will add 3 seconds to this number. It would be 68, the first number will not be changed, and 12 minutes will not be changed from here, and then the 26 seconds here, I will add 3 seconds to it. It would be 29, and so on. For here, this case, it would be 94, 42, and I will add to 8, 3, it would be 11 here. Okay, and so on. For here, 102, 58, and then I will add 3 here, and for this case it would be 94, 6 minutes and 30 seconds. So now just let me clean everything and write them down in a nice way. Now here we have all the answers now, and after you do this you can check your answers. I will check just that the summation of the corrections would be 12, like here, and also I will check that the summation of my corrected angles should be 360 degrees exactly. This is an important check. After I corrected the values of the angles, now the corrected angles should be 360 degrees like this number. And finally, before we completely finish the angles, we are going to calculate the angular accuracy. This is very simple. The angular accuracy in seconds is given by this relation, which is plus or minus the error value divided by the square root of n. In this case, plus or minus the error value in our case, it's 12 seconds divided by the square root of n, and number of the angles. In our case we have 4 angles, so it would be here plus or minus 6 seconds. So this is called the angular accuracy. Okay, now we have completed the first stage of the work, which is checking the angles and correcting them, and also we have calculated the angular accuracy. Now let's move to the second stage, which is calculating the whole circle bearings. Don't forget, the whole circle bearing is just an angle from the north to the measured line. If we are working on a line AB, this is the whole circle bearing. This is what we are calculating now. It's an angle from the north to the line. We've been given the first whole circle bearing for line AB. Now our task is to calculate the whole circle bearing of line BC, CD and DA. And this is the relation that we are going to use to calculate these whole circle bearings. For example, the whole circle bearing of BC, this one here, it would be the whole circle bearing of AB, which is given here and known. This is the whole circle bearing of AB, plus 180 degrees plus the angle B, the corrected value of angle B. This is the corrected value of angle B. Okay? So again, to calculate the whole circle bearing of BC, this value, it is the whole circle bearing of AB, this one, plus 180 degrees, plus this value here, the angle B. Okay, so I will write down here 100 degrees, 11 minutes, 22 seconds, plus 180 degrees, plus angle B, which is 94 degrees, 42 minutes, 11 seconds, and the answer in this case is 374 degrees, 53 minutes and 33 seconds. And because of that, we have this number. If you have an answer like this, this is absolutely not correct, because the whole circle bearing shouldn't exceed 360 degrees. So if you have something like that, please do subtract 360 from your answer, okay, to get the right whole circle bearing value. So in this case, because I have my answer here is greater than 360, so look at this important note here. If the calculated whole circle bearing is greater than 360 degrees, do subtract 360 degrees. Okay, take away 360 degrees. So I would just simply say minus 360 degrees. So, and the final answer in this case would be 14 degrees, 53 minutes and 33 seconds. So this is the whole circle bearing of BC. Okay, I will write it down here, 14, 53 and 33 seconds. Okay, and so on, guys. Now to calculate the whole circle bearing of line CD, it would be the whole circle bearing of line BC, this number, plus 180 plus angle C. And if the answer is more than 360 degrees, take away 360. If it's less than 360 degrees, write it down here as it is. Now to calculate the whole circle bearing of DA, the same, it would be the whole circle bearing of CD plus 180 degrees plus angle D from here. And then I will write down the answer here. Now let me calculate these values and get back to you. These are the final whole circle bearing values, guys. The first one is given to us. We started from a known value to calculate the unknown whole circle bearings. This is the whole circle bearing of BC, the whole circle bearing of CD, the whole circle bearing of DA. And as a double check, you can recalculate the whole circle bearing of AB again, and it should be the same value that we started from. How to calculate the whole circle bearing of AB again? So this is the same relation here, but instead of BC you will say the whole circle bearing of AB, which is the whole circle bearing from here of DA plus 180, now plus angle A, and this should be the same value that we started from. This is as a double check for your work, if you like. So by doing that, we have calculated the whole circle bearings for all the four sides, and we are going now to move to the next stage, which is calculating the departures and latitudes. Calculating the departures and latitudes is very simple using these relations. So the first relation, to calculate the departure of any side, for example AB, you will use the relation the length of AB times sine whole circle bearing of AB. To calculate the latitude of line AB, the length of AB times cosine the whole circle bearing of AB. For more information about the departures and latitude, please do watch the previous video, which is Traverse Adjustment Part 1. I explained in details what is the departure and the latitude. Okay, so let's try the first one, departure of AB. I would like to calculate this value here, departure of AB. It's the length of AB times sine whole circle bearing of AB. This is the length of AB, yeah, times the whole circle bearing of AB. This is the whole circle bearing of AB. It's an angle, so sine this angle. This is very simple, yeah. So in this case, 107.804 times sine this value, 100 degrees, 11 minutes, 22 seconds, and then we will get the answer. In this case it is 106 meters point 104. So this is in meter, guys. So this is a distance. The departures and latitudes are distances. And similarly for the latitude, it would be the length of AB, the same length here, times, instead of sine we will use cosine, the same angle here, and then we will get the value minus 19 meters point 071. So this is the latitude of AB. It would be written here. So the departure is the length times sine this angle, the latitude is the length times cosine this angle, and so on. For line BC, the departure here is the length of BC times sine whole circle bearing. The latitude here, it would be the length times cosine this angle, and so on. Let me calculate these values for you now. And these are the final answers for the departures and the latitudes. Now after we calculated all the values, all the departures and all of the latitudes, guys, there is now a very important step now. We are going to find the summation of all of the departures here. This is the summation of all of the departures, and we are going to find the summation of all of the latitudes. I have here two positive values and two negative values, and here the same. This is negative, this is negative, here we have positive values. So I find the summation of all of these. It would be here in this case 106.104 plus 20.402 minus 68.027 minus 58.454. The final answer in this case 0.025 meters. All of these here in meter. So this is the error value. This is the error value in the departure direction, and this is the error value in the latitude direction. So here, for example, this value, let's say 0.025 meters. This is the error in the departure direction along easting axis, and this is the error value along the latitude direction, 0.010 meters in this case. Okay, so this is along the northing axis, the latitudes. Now we are going to calculate the linear error, which is this value here. This is the linear error using this relation, the square root of the departure error squared plus latitude error squared. So this value, the square root of this value squared plus this value squared. This is easy. So in this case, the square root of, this is called linear error, the square root of 0.025 squared plus 0.010 squared. Let's calculate that. 0.027 meters. This is the linear error. Okay, now after we have calculated the linear error, guys, we are going to calculate the linear accuracy in a form of 1 to something, like 1 to, because usually in the projects you would be given, for example, an allowable error, for example 1 to 1000 for linear accuracy. So you need to calculate your linear accuracy in this format, 1 to something, so that you can compare your error against the allowable error. So here in this case, this number, guys, means 0.027. That means when we measured these four distances here, we've done this error, okay, because this is a linear error. When we measured all the distances, and this is the summation of all of them, 374.509, when we measure the whole distances, we've done an error of 27. Okay, so the error is 0.027 for a distance of 374.509 meters. Now to convert this to be in simply I will divide this by 0.027 to convert it into 1, and I will divide this, of course, by 0.027, and in this case it would be 1387. So this is the linear accuracy, 1 in 13,870. Okay, so if you have in your project like the allowable error to be 1 to 1000 or to any number, you can compare these two numbers against each other, and then you can decide if your measurements are accurate enough in terms of linear accuracy. So for this project I can say, okay, the linear accuracy is 1 in 13,870. Now guys, we have calculated the linear error and the linear accuracy, and then now we are going to move to the corrections. After we calculated the departures and latitudes, we are going to calculate the corrections. Okay, we have an error. Don't forget that we have an error here for the departures, we have an error for the latitude. We have to correct these errors now, to distribute these errors for the four sides. These are the relations used for calculating the correction value for each side of the traverse. The correction to departure, for example, here would be the total departure correction times the length of the side divided by the perimeter. Okay, so in this case, this is the total error for the departures, and this is the total error for the latitudes. And don't forget, the sign of the corrections is opposite to that of the errors. Here we have this error is positive and this error is positive, so the signs of the corrections should be negative. So the total error is 0.025 for the departure. The total correction would be minus 0.025. Okay, so this is the total departure correction, would be the same value of the error but using the opposite sign. And here for the latitude, the correction to the latitude is the total latitude correction, which is in this case this value minus 0.010. Okay, the perimeter value, summation of all of the distances, yeah, it is 374.509 meters. The same here. So in my case, the correction to all the departures would be negative. I will write here clearly this should be negative, and the correction to the latitudes should be negative. Okay, I will repeat this point because it is very important, guys. Here I have calculated the total error of the departure. It is plus 0.025. The correction should have an opposite sign. So in this case, the correction to the departure should be minus 0.025. This is the total correction. Now we are going to use this relation to calculate the correction to each side. Okay, so for side AB, for example, I will apply this on one side and then you can do it for all of the sides. If I would like to calculate the correction to departure for side AB, it is the total departure correction, this value, minus 0.025 times the length of the side. What is the length of side AB? This is the length of side AB here, this value, 107.804 divided by the perimeter, this value, and then I will get the answer. So in this case, the answer would be, I will write it down here, minus 0.007 meters. So that is 7 millimeters. Okay, so to correct the departure value that I calculated here, I need to take away 7 millimeters from this number. Now let's calculate the correction to latitude for line AB. Now this is the total correction of the latitude, this value, minus 0.010. The length of the side, the same length, 107.804. This is the length of line AB, divided by the same value, and then in this case we will get minus 0.003 meters or 3 millimeters. So that means to correct this value here, the latitude of AB, we need to take away from this number 3 millimeters. And here I will write, this is minus 0.007 for the departure, and then this is minus as well, 0.003 for the latitude, and so on. I will calculate now for line BC the correction, and every time here, guys, just the only thing that would be changed, the length of the side. For line BC you will use this length. Let me just clean some of the numbers. So here, if I would like to calculate the correction to departure for line BC, for example, and correction to latitude for line BC, the total departure correction, the same value will not be changed, the perimeter will not be changed, The only thing that would be changed, the length of the side, because we are working on a different side now, which is BC. The length of the side BC in this case 79 meters, 0.385. Okay, and this is the same length that would be used here. So here the correction to latitude, the same value here, and the length of the side would be 79.385, and so on. And in this case, if you calculate these two numbers here, it would be minus. Here it would be minus before I do the calculation, because I know here plus, it would be minus here, the opposite. So I will do the calculation now, and this would be 0.006 and here 0.002. I will write them down here, and so on every time just you would like to change the length of the side. Okay guys, now these are the final values of the corrections. Don't forget the negative sign here. This is for line CD, this is for line DA. And also you can check your answers. Don't forget to check. The total error for the departure is 0.025, so the total correction should have the same value. The total error to latitude 0.010, the total correction should be 0.010. Now let's move to the next stage, which is calculating the corrected departures and latitudes, which is very simple in fact. For the departure, this is the departure value, okay, and this is the correction to departure value. So here the corrected departure is the departure value plus the correction, and the corrected latitude is the latitude value plus the correction. This is very simple. So 106.104 0.007. So it would be in this case 106.097. I just have to take away 7 millimeters from this number. So 7 millimeters take away from this number. Now the correction to latitude, which is the latitude value minus this one, yeah. So the latitude value minus 19.071, okay, minus 0.003. It would be in this case minus 19.074, and so on. You will use the same. So the correction to latitude here 76.718 minus 2 millimeters. You write down the number here. And for the departure, the same thing. The correction to departure is this value minus 6 millimeters. You write down the number here, and so on. Calculating the partial coordinates or the corrected departures and latitudes is very simple. You have the departures and latitudes here, you have the correction values here. Just add or take away the correction values to the original departure and latitude values. Okay, so let me do the calculations for you. Now I have calculated all of the values, all of the corrected departures and latitude, as you can see here. Just always judge your numbers. Here, for example, I would like to look at this number here. This is the latitude, minus 39. I will take away from this number 3 millimeters. It would be within the same range. The difference between them would be 3 millimeters. Okay, and then add a check as well at this stage. The summation of all of these numbers now, the corrected departures should be 0. The summation of all of the corrected latitudes should be 0. The summation of all of these should be 0. The summation of all of these should be 0. And that means you have distributed the error, the linear error that you made. Now you have distributed this value and this value. Okay guys, now the last stage, which is calculating the total coordinates. Let's move to it, which is this one here. After we have calculated everything, this is very straightforward one. You know that always we have to start from a known coordinates. In this case, we've been given the coordinates of station A, 900 for the easting and 800 for the northing. Now we are going to calculate easting and northing of B, easting and northing of C, easting and northing of D, and then we can double check by recalculating easting and northing of A. This is the relation for calculating easting of B, which is easting of A that we started from, plus the corrected departure value of AB, of line AB. So this is easting of A, 900, plus the corrected departure value. This is the corrected departure value, 106.097. So 900 plus 106 would be 1006.097. So I will write it down here, 1006.097. Sorry, 0. And for the northing, so northing of B here, guys, would be northing of A, which is 800, okay, minus 19, which is the corrected latitude, okay, minus 19.074. So I will write down the answer here to be, in this case, 780 point something, okay, and so on. So now for C, easting of C here would be easting of B from here plus the departure, and northing of C would be northing of B, this value, plus the latitude, and so on. Okay, I'll do the calculations now, and then you can do your calculations on your own to double check the answers. So these are the final answers, guys. These are the coordinates of B, C, and D, and this was our aim from the whole calculations of the traverse. Now we have our traverse ready, we have the coordinates of these 4 stations, and now we can use them to survey this area or to set out any structure that we need, etc. So these are the coordinates of the traverse stations B, C, and D, and that was the whole aim of the whole traverse calculations, to calculate these numbers to a very high level of accuracy. I have an important note here. Throughout the calculations, guys, because of rounding the numbers at some stage here or here, rounding these numbers can just produce some kind of differences within 1 millimeter here. Okay, so don't worry so much if you have a difference of 1 millimeter. You can just double check your corrections to distribute that 1 millimeter in a good way in this stage, for example. So if you have sub-millimeter answer, for example here, if you have 0.002718, you will have a number like this. You can round this up to be 3, okay, and then just make sure that the summation of these numbers would be the same value of the errors, okay. So by doing that, guys, we completed the calculations of the traverse, and now if you have been asked, for example, to draw this traverse, it would be very easy now because you have done all of the required corrections. You can just draw, for example, a coordinate system, easting and northing, and then now you have 4 points, just 4 points with their values. You can just represent these 4 points on a coordinate system. So this is point A, this is point B. You have their coordinates, the value of the coordinates of each one of them, just you can represent them. This is, let me say, point C, and this is point D, and then you can join these numbers by lines. Okay, if you would like to draw straight lines like these, okay, you can do this on a graph paper. That would be very easy and nice as well. And then if you would like to double check these angles, it would be very easy for you. So just now, again, you have just coordinates of each one of them. You have easting and northing of C, you have easting and northing of D. Just represent them on a coordinate system like this, and this is your traverse that you have completed. Okay guys, thank you very much for listening. Today I tried to explain in details how to complete the traverse solution, traverse adjustment from A to Z. As you can see, it is little bit very long process, but it is an easy, no complicated maths in it. Just using very simple relations to complete the whole calculation until you achieve your aim, which is calculating the final coordinates of your traverse to a very high level of accuracy. I hope that was useful, guys. Thank you very much for listening and enjoy your time. Bye now.